Thanks. Welcome to my talk. I'm a PhD student from the Center for Vision, Speech and Signal Processing of the University of Surrey in the UK. And I'm going to talk about some face stuff and C++. So I just have a couple of slides about our center, and then I'll get into the interesting stuff. So we're located in the southeast of England. We're one of the largest UK centers for vision, speech and signal processing, around 30 years old at the center. We are 120 people, 70 PhD students, and yeah, we have quite a lot of projects running. So we do all kinds of stuff like medical imaging, detecting abnormalities in medical images, segmentation of like MRI images, CT images, analyzing of breathing motions. We do sound stuff. So for example, here, how can you bring like the listening experience from a stadium to the comfort of your home? Then we do a lot with like 3D video. We have a recording studio, like for example, record actors from different view angles, and then reconstruct the whole actor or the whole scene in 3D. We do sign language recognition, tracking, face tracking, obviously, people detections, all these kinds of computer vision and audio signal processing stuff. So I'm a PhD student there. I'm working on faces, and I'm mostly interested in how to reconstruct a face in 3D from a 2D image or a 2D webcam videos. So like no 3D camera or 3D information, just like pure 2D video. I'm very interested in modern C++, obviously. And I'm also quite like, I really like open and reproducible research. And so if you work in academia, often like you read a paper, and then when you really want to re-implement that paper, there's really so many details not clear. So I think if we put like our software online, that's a lot better. So we've recently open sourced 2 libraries, and I'm only going to talk about that and like some challenges and problems we had with C++. So face tracking and reconstruction. Usually you have some kind of video or an image, and what we do first is we detect the face of a person in the image, and then we detect some facial landmark points. These can be like eyes or the nose, or here like around the face, these kind of interest points. And from these points, we have a very accurate location on where the face is. So from there on, we can do more processing and, for example, reconstruct the face in 3D from the 2D image. And this has all kinds of applications, from getting a frontal view of the face. Somebody might look to the side, and we might want a frontal view of the face. Face recognition, obviously, like expression analysis. We use it in human-robot interaction, so it's running on a robot, and so the robot knows who it's talking to, basically, and where the person is looking to. Yeah, all kinds of applications. So in the first part, I'm going to talk like about our landmark detection and the library we developed in the process. I'll spend a few minutes on the algorithm, so you know a little bit what it's about, and then some interesting C++ bits. And just towards the end, I'll spend like 2 minutes on the second library on 3D face reconstruction. And our main goal with this is to make 3D face models and research with 3D face models a lot more widely available. If you work in computer visions or faces, you might know that like a lot of algorithms are based on simple two-dimensional models. You might have heard of like active appearance models, active shape models. These are kind of the most used algorithms. And 3D algorithms are like a lot harder to use. They require, first they require a lot more effort to build a model, a 3D model. That's a lot harder. And then also to use that model is a lot harder as well. So we kind of want to fill in that gap. So recently, there has been a class of algorithm that is based on linear regression that is very successful for 2D landmark detection. And how they basically work is we have a face box, which would be the blue box, which comes from a face detector. And then we have trivial initialization. So we just put the red points somewhere. The red points might be a mean face or something that we just put inside the face box. And from these red points, we would then like to go to the true location, so to the green point. For each point, obviously, we would find the true landmark location. And so these algorithms are called regression-based methods, supervised learning. And basically what happens is you have a bunch of training data. And from this bunch of training data, you learn from the image information how to get to the true location. And we've already had some Matlab code of this, but all our 3D face software was in C++, so we kind of chose to re-implement this in C++. And also, it turns out that these algorithms can do a lot more than just 2D landmark detection. So we kind of wanted like a very sustainable implementation of this that doesn't just work for facial landmark detection, but for a lot more applications as well. So you might know linear regression. Basically, the formula y equals mx plus b. So we have some kind of input variable x, and we have a linear relation between the input variable x and the output variable y. I think this is, by the way, the only formula in my talk, so don't worry. And we want to find an m. We want to learn a m basically from training data, so that when we input like a new x, we can predict the y. That's basically what we want to do. And if we change this formula very slightly, we get this, which is basically what we are doing and learning. So we have this matrix A that we want to learn from data. And we have this f, and this f is basically a function that takes I, the image, as input, and S would be the current location of the landmark, so basically the current shape. And from that, this function f, in this case, basically extracts the red neighborhood, so the neighborhood of the landmark location. And from the information in this neighborhood, we would like to predict on where to put the point, so on where to go with the landmark point to eventually converge on the true location. And this is based on the method mentioned in that paper. So we have like a few hundred or 1,000 training images that are like hand labeled, so we know the true location. And each of these images will basically be one row in a linear system of equations. And then we solve that to basically get our matrix A. So as I said before, it turns out that this algorithm can actually do like a lot more than just optimize for 2D landmark locations, because like the parameters on the left side, which were like the shape locations, they could be anything. So if we were working with a 3D model, we're probably not interested in like finding some 2D pixel locations, but we would be more interested in finding the 3D rotation and translation parameters of the 3D model, and basically, because these parameters, they tell us where to put the model so it matches the face in the image. And of course, in this case, the function f would be different as well, because it would need like access to the 3D model. And in this case, the f would basically be kind of the whole rendering or projection of the 3D model to 2D. So we wanted to implement this in a way that it works in all these cases. So we are getting into some code now. So basically, this function f that models this, basically going from that parameter space to the space where we optimize. We model this as a function in the code. which is pretty cool, because if this function is like a trivial thing, we can just define it as a lambda function, like in place, and it's very easy to use. And if it's something more complicated, like 3D stuff, 2D landmark detection, we could make this function object with some state. It could contain the 3D model, and it works exactly the same way. So to go to some code, in case of the landmark detection, we would have a function object, and let me just see if I can get the mouse. Okay, we would have a function object that takes all the images on creation, because during runtime it needs access to the images, and then the generic part is basically the parameter input, and the parameter input would be our 2D landmark locations of the face. And then this function here, it's very simplified, would basically extract the neighborhood, some kind of, we don't directly use the RGB information. There is basically something called local image features or hog features. They basically do something smart with the RGB information. They calculate the gradient of the image in different directions. And then this function returns a descriptor of this neighborhood, and from that we can start the learning process. And I'll show you some other examples of that later. There may be some things you don't know. For example, this mat. Could I maybe get a quick show of hands who has used OpenCV before? Okay, that's a lot of people. So for the people that don't know, this mat is from OpenCV. And I thought, as this is like a C++ conference, and for the people that don't know yet, it's probably interesting to quickly have a look at that. So CVMat is basically the matrix or image class of OpenCV. It behaves like a smart pointer, like a shared pointer basically. And it contains a header that has basically the dimensions of the matrix or image and some flags. And to use it is pretty easily. So the first row would create a 5x5 matrix of floats. And then on the second line, we can get like a sub-range of this matrix. So here we would get only the first two rows of that matrix, and no data is, so basically just we create a new header, but the underlying information is the same. We just have a header that points to a different location in memory. And the last line is if we want to get an element. So, and images are basically matrices, so there's no difference between images and matrices. So we have this transformation function, and the other things we need is a learner, basically, a linear regression class that solves this system of equations. And then we have a optimizer that takes all these things and puts them together. So this optimizer, it takes the learner, the regressor, and it takes this projection function, which it applies to each image basically, and from that we can start the learning process. So in code, it basically looks like this. We have a bunch of training images. We have a bunch of training landmarks, which would be a matrix with one row for each image. We have initialization values of these landmarks. We have this function that extracts the neighborhood. We say we want to learn 5 regressors. So we actually not only learn one, but we can learn several that will be applied in series, which will increase the performance. And then we have the optimizer. We can specify a function that gets called after each iteration. So basically we can say, okay, after each iteration, we would like to calculate the training error, and it will print that out. And then we can start the training and afterwards store the model. So to use the model is equally easy. We use Serial. Serial is a serialization library. I will get to that in a minute to store and load the model. And then to run the model is just loading the images and run the detect function, which will return the landmarks. And that will give you something like this. And as I said before, our goal was to have like a very generic implementation of this. So after we finished that, what we actually did is we could just switch out this projection function f basically by another one that uses the 3D model and replace the 2D landmark coordinates by these 3D parameters. And we just recently got a publication out of this that I'm going to present next week. So it turns out that this works pretty well. So some C++ challenges with that. How many of you have worked with Matlab? Okay, oh, quite a lot, okay. So to solve this linear system of equations, we might have a lot of images, like a few thousand images. And we might have like a lot of landmark points, so our neighborhood is pretty big. So basically the matrix that we get can be pretty large, like 15,000 times 8,000. And to solve a linear system in Matlab, you can just do like a\b, and it will give you the result. And this function is incredibly good. It's like fast, it's parallelized. It automatically chooses which algorithm to use to solve this system of equations. So there's like QR decomposition, LU decomposition, all kinds of algorithms that you can apply. It just chooses like the best one. And it also warns if the system is not well conditioned. So what obviously can happen is that like the system doesn't have a solution, or that it is underdetermined. So we have like less equations than unknowns, and all this kind of stuff can happen. And so to solve a matrix of this size in Matlab takes like 3 minutes. And when we first tried this in C++ with various libraries, it was more like a few hours. And I thought at first that there was something wrong, but there wasn't. So there's, in C++, obviously, like you have to choose a library. Which library are we going to choose to solve our systems? It turns out that OpenCV is horribly slow for matrices of this size. It's good for matrices of like 200 times 200, but not for this kind of stuff. There's libeigen, which is pretty good. There's other things like boost, ublas, I guess. We chose libeigen, but even libeigen had like 5 or 6 or 7 different algorithms that we need to choose from. So the first one I chose the best one, of course. It turns out, or like the most accurate one, it turns out that the most accurate one takes an hour to run. So it took me a while like to figure out which one is good. Obviously the ones that are fast have some drawbacks. For example, one drawback is that they assume that the system of equations is invertible. So if you give it something that's potentially not invertible, then I guess anything could happen. But luckily, this is not a big problem for us because we calculated the training error in each iteration. So if our system gets like not solvable, then we'll know because the training error gets really high. Also, not all of these run in parallel, and it turns out you really want to have something that runs in parallel. So yeah, this was kind of one bit that took us some time to figure out. Now that we know all this, it's pretty easy, but like compared to Matlab, where it's just a one-liner, I think we would have wished that it was a bit easier in C++. Another thing that was that we wanted to import our models from our Matlab code, and this is not fun. Matlab has this Matlab compiler SDK, which is, I looked at it last like a year ago. Maybe they have improved, but I don't think so. It's like this ugly, hard to use C API, and I just said I'm not going to use that. So the second solution is like text files and manual parsing. And we kind of tried that in the beginning, but it turns out that somebody changes the Matlab code and then you need to change all the writers and the parsers and everything, and it's just like a real hassle. So we actually, we haven't really done that. We train all our models in C++ now because it's just so inconvenient to get data from Matlab to C++. So I'm very open for suggestions here if anybody has a good solution. But even like storing the models in C++, we had some problems. The task seems pretty simple. We train a model in C++. We want to upload it and have other people use it. We tried, and we don't want to do this by hand. We want to use a serialization library, obviously. So we tried some XML and text formats, but it was kind of out of the question because our models get too big. And most serialization libraries don't generate the best XML if you have like a lot of floating point numbers. So it would generate like one tag per number. So it means you have a huge overhead. So our models get like a few hundred megabytes in size, and that's not what we want. So we tried the Boost serialization library first, which is a really, really awesome library. But we had some problems. I work with a fairly recently Boost version on my laptop, and a lot of my users and on our lab computers have older Boost versions. So if I train a sort of model, they can't load it. And so now you could say I could just install an older Boost version on my laptop. But first, I don't really want to have several Boost versions on my laptop. And second, the problem is that the old Boost versions actually don't compile in newer Visual Studio versions. So that's also really not an option. So I found Serial, which is a pretty cool C++11 library for serialization. It's header only. And we can embed it in our own source code. So we basically get rid of all these problems. And the syntax is really similar to Boost, so it took me like 5 minutes to change it. What's not so nice is that this library has no update guarantee. So they say like, yeah, if you update our version, like or your previous models might not work anymore. But I guess you can't have everything. So yeah, the result of this is this supervised descent library, which we open sourced. Which is basically the first part of my talk. So very quick to the 3D model stuff now. We basically did the same what I described with 3D models. We have a library that handles the 3D model. So we have this 3D face model. And is it moving? Yeah. So basically the model is trained from example 3D scans. So we can adapt this model to different people. So if you look closely, you can see that here it's mainly like the size that increases. Here it's like the width of the face that increases. And here there is some more local details that are modeled, I think more up here. So basically we can adapt this model to a specific person, which is what we want to do during like face detection and face tracking and 3D reconstruction. I'm not going to go into details here. We have a simple representation of the model in the code. We can fit the model to a new image. I will show you an example of this pretty soon. We release that as well as a library. And we include the low-resolution shape model. So basically, we give the users a low-resolution model so that they can immediately start coding and using our stuff. So let's get to a demo. Basically, the demo shows these two things combined after each other. And now I have to switch that to the external monitor. So basically, what you see here is the detected landmarks. Here you can see the 3D face reconstruction, and that's basically some internal information here, which I'm showing because it's interesting to explain. So basically this guy is looking to the left, right? Like from from his point of view. And so what we do here is basically we don't use the information from this side because obviously we don't know what is happening here. And if I run the video now, you can see if he turns, we start to fill out information here as well because we get some information here. We merge this information, and here is basically just a 3D rendering of the current 3D model. And let me quickly show a second example. That's a bit slower because the resolution of the video is a lot higher, and I think currently we don't like rescale the image, so it just runs a bit slower. And what we can do, we can press a button, and then it saves an OBJ to the hard drive, and then if Windows does what I want to do, we have a, sorry, I'm looking for my mouse. We have a 3D model of that face, basically. Okay, let's get back to the presentation. So to sum up, we think we have created like two simple to use modern C++ libraries, which really fill a gap looking at what's out there. There is quite a lot of alternatives out there for 2D landmark detections. Some of them are really good, but without source code. Some of them run like only either on Linux or Windows. And most of the open source ones that are available are kind of really old C code, or C++ code that is really C code, and it's not really that easy to use. There are, of course, a few notable exceptions and some really good other libraries as well in other languages. One of our main open work package is to make it work better with facial expressions. If you had a very good look at the video I showed, you probably noticed that like when he opens the mouth, it doesn't track the landmarks very well when the expressions get strong. Header-only libraries are great. We've actually switched one of the libraries. It wasn't a header-only library, and then we switched it because header-only libraries are really a lot easier to deal with. For example, if you want to run stuff on like exotic platforms, like I've tried to make a web demo with emscripten, I'm not sure how to pronounce it. And there it's just a lot easier if you have header-only libraries. You can just make an app, include the library, and yeah, so obviously it increases compile times, but I think if like the libraries are small, then it's kind of really good. One thing we thought about is if we should, it would maybe be nice to integrate some of the stuff into OpenCV, if they're interested, of course. On the other hand, we've also have opinions that are like quite on the other side of the spectrum. Getting rid of OpenCV would be nice as well, because it turns out that in some of these web and mobile experiments we did that it was a bit hard to get to run OpenCV there. So I don't really know where to go from there. OpenCV is doing a lot of effort to run like on Android and iOS, but it's still not all perfect. So I want to thank the whole team. There's a lot of people involved that worked previously on the model and have contributed to the software. And yes, some references, and thank you very much for the attention. Okay, questions? Yep, please.
You said that you have problems when you see facial expressions.
Mm-hmm.
Do you get problems when there's illumination changes, like the lighting changes?
We don't have so much problem with illumination because if you use something like hawk features or even learned features, they're quite invariant to light changes. Of course, if you have like a really hard light gradient, sometimes there's problems, but in general, these image features are quite invariant regarding light. And I think I have to repeat the question, right? So the question was if we have problems with varying light. So if you have strong varying light, yeah. Yeah, you first.
Did you mention what eigen method you used that would work for SPD for your case?
The partial pivoting LU decomposition. Yes, it was the one that had the orange bar, because it's one of the only one that runs in parallel. If you compile, you have to add -f OpenMP, and then it parallelizes automatically. We had the constraint that in the equation system we solve, our right-hand side, basically the B, is a matrix as well. And also not all of these algorithms run work if your right side of the equation is a matrix. And so the partial pivoting LU decomposition, it doesn't check for invertibility, but as I said before, that's not so much of an issue because we see that in the training error. And the question was which decomposition we used with eigen. Yeah. Did you have a question?
I have a question about what methods did you use for solving linear regression? So it looks like you need to inverse matrix, but it's not exactly necessary for gradient descent or something else.
So the question was what method we used to learn the linear regressors, that inverting the matrix is not necessarily something we have to do. Yes, there are some iterative algorithms. I haven't really looked into that because we basically came from the Matlab side, and in Matlab all we ever did was solve the system of equations. One thing to note there is that we don't invert the matrix, so inverting the matrix and solving the linear systems are two different things. So you can solve the system more efficiently directly for your right-hand side of the equation instead of inverting the matrix. So that gives you some performance speed up. But of course, there are iterative methods. I think you first. Yeah.
So I can see why you didn't want to use Matlab. Having used it myself, but the performance trade-off is a really big issue, right? Have you looked at how Octave implements matrix algebra? Like, it's open source and also C-based, but I don't know if the performance is.
Okay, not really, because so I actually like Matlab a lot, and I'm a student, so everybody at the uni has it for free. That's obviously a different story in industry. Yeah, what was your question? Sorry.
Do you know if the performance of Matlab versus Octave is like comparable? Because Octave is an open source project, and the C component could be integrated with the C++ library.
Okay. So performance of Octave versus Matlab, no, I haven't used Octave. Yeah. Okay, I think one more. Yeah.
So the OpenCV maps container is kind of not what I would call, I guess, good C++, because they chose not to do a templated type. So I guess, what are your thoughts on that? I think you had a slide at the end on
OpenCV?
getting rid of OpenCV. And like, what options are you considering?
So one option would be just to use libeigen. One problem is that we need something to load images, and OpenCV has just like IMRead. So I've had a look at image loading libraries. Most of them are like C or can only load like one type of image, like or using libpng manually or something like that. I don't think that would be a lot of fun. Loading the images is a problem. Yeah, it would be awesome to have that in the standard library, right? But regarding the OpenCV type, so they don't template their type, their matrix on the type. One advantage of that is that you can convert between all of them, and if you work with images, this is kind of an advantage. So you load like a 3-channel image, and then you can convert it to a 4-channel image with alpha channel. You can convert it to like a floating point image, do some operation. Yeah, but I mean, they made some design decisions that you can agree or disagree with, or even say it's not the best C++ maybe. Also, the overhead of the mat header is actually quite large. So I think it's 96 bytes or something like that. So if you have like a few thousands of them or a few 10,000s, you have to watch out. Can take a lot of RAM. So, but I think it works. So. Yeah.
Can you go back to the slide where you talk about the regression software?
So this one or next one? I think maybe previous one. This one?
Much
Earlier, okay. Yeah, I think that was. Not really. I think it was this one, right? This one was the one where we've looked at some methods for solving the system. No, the solution was that we used the partial pivot LU decomposition from Eigen because it parallelizes, it's pretty fast, and it doesn't check for invertibility or something like that, but we are okay with this. So this turned out to be pretty good. I think it... Yes, so the question is if it's any close to the 3 minutes from Matlab, and yes, it is. It is... I haven't measured it, but it runs within minutes as well, yes. For very large matrices. I think it's probably a bit slower, but not that much.
You mentioned using Scripting to do a web demo. Was that successful, and what kind of performance did you see there?
That was not that successful because I had some problems with OpenCV and a little bit with Boost. So I haven't finished that, but I think I will pursue that further. It's pretty cool. Okay, I think that's it, and we run out of time. So thanks again.